in Chapter 14, we're looking at aqueous solutions and the compounds that can form in those aqueous solutions. So the first thing we have to know, and something we've already talked about, is that when we have ionic compounds, we can have these as ionic compounds. These are both solids. They're both ionic. There's an alkali metal, or an alkali earth metal in calcium's case, bonded with a halide. So a classic ionic compound. Now we put those in water and they dissolve. What happens is the process is called dissociation. We actually get positive cations and negative anions. Cations, anions. So they'll break apart into solution. They'll dissolve because the water will coordinate itself around those particular ions. Remember, water is very polar. So notice around this chlorine, actually, if we can zoom in, you can see in this image that around the chlorine, here I'll clear the ink, around the chlorine, you'll notice that the hydrogen guys, which are the positive guys of the polarity in the water molecule, are associated around that chlorine. If we look at the sodium, notice sodium, which is positive, is attracted to the negative side of that water molecule, the oxygen. So they do dissociate, they separate. So really, in solutions, the whole point of this is in solutions, when we have solutions, we have to think of them not as sodium chloride, but when they dissolve as sodium ions and chloride ions, calcium ions and chloride ions when they dissolve. The other thing we have to be aware of is the amounts that are present. Okay, if something dissociates 100%, and most ionic substances do, say we have sodium chloride, dissolves 100% dissociation, and we have 1 mole of that, well, that gives us 1 mole of sodium ions and 1 mole of chlorine ions. Now, we have to be a little bit careful about how that formula is written, because if we have 1 mole of calcium chloride, notice, that dissolves in water. We have 1 mole of calcium ions, but notice 2 moles of chlorine ions. Because of the 2 there, they actually both separate. So just be aware of what the formulas are in case there's some questions about how many moles of ions are formed. We know it correctly from the formula that's present. Okay, now this is the interesting part that we can have in reactions like this, is because now, say we dissolve a couple things. Let's look at these equations first. We have sodium sulfide, which is a solid, but will dissolve in water. Or, I'm sorry, I called it sodium sulfide. This is ammonium sulfide. We get ammonium ions, and we get sulfide ions. Okay. Here we have cadmium nitrate. It's a solid ionic. It also will dissolve in water. We'll get cadmium ions and nitrate ions. No problem right now, right? Everything makes sense. Everything is clear. Wonderful. So, notice in one test tube, we have sodium ions floating around with ammonium ions. In the other one, we have nitrate ions, and we have cadmium ions. Okay, but now we mix them together. So now one is poured into the other, and look at what we get. We get what's called a precipitate. A solid precipitate forms. Now, why does that happen? It is because we had this dissociation. So now, once we mix these together, we actually have sodium sulfide ions, ammonium ions, nitrate ions, and cadmium ions, and they're all mixed together, and they're all free to react. So even though they are all soluble separately in their separate compounds, now that we mix them together, we found a combination that is actually insoluble. So they're going to bond together and form an insoluble compound. Okay, so let's look at what we have for this one. Again, let me delete all my scribbling. So, really, what we have is we have these ions present. And notice this tells us what our solid is. So, we had ammonium and sulfide, and that dissolved. And so no, they're all free to react. So even though those two individually before the reaction were soluble, again when we mixed we had a solid. So what we have to figure out is, this one tells us what it is, but how do we know that? Well, we know it's not ammonium and sulfide because those were soluble before. So what we do is, this is kind of our classic double replacement reaction. We take our ammonium and we try it here. So what we'll do is we'll take those options and we'll merge them together and write the actual equation, because again, it's this double replacement reaction. So we have that ammonium sulfide, right? And it's reacting essentially with our cadmium nitrate. And what we get now is, those are the two different options that we could get. We could have a cadmium sulfide, and we have an ammonium. So if we wrote the full balanced equation, then let's write out, this is aqueous, this is aqueous because they both dissolved in water, this now is our solid, and this is aqueous. Last thing we would want to do is balance it. Notice we had two ammoniums 2 nitrates, there needs to be a 2 in front there. So that's our balanced equation. That, however, is not a net ionic equation. Sometimes they want you to write a net ionic equation. What a net ionic equation is going to involve is just the things reacting. So this is our balanced equation. Let's edit it to get net ionic. Because if we look, notice sodium here is aqueous. That means sodium, I keep calling the sodium, ammonium is aqueous. That means it's dissolved in water. It's really an ammonium ion floating around. Over here it was the same. So really it didn't do anything. So if we were just writing what's called our net ionic equation, we're going to cross out all of those things that are aqueous on both sides that really haven't changed. Here we have nitrate. I'm going to cross that off. And I'm going to cross it off over here because, again, it was aqueous. So it really hasn't changed from one side to the other. So in our net ionic equation, we have only the things that change state. So we had cadmium as an ion, and it reacted with sulfide ion, and it formed cadmium sulfide. Now, why do we do that? We do that because, again, those aqueous ions are still just floating around. They did not really react. So it's not really bonded to the nitrate, even though we represented it as that. It's really just floating around as an ammonium ion. The nitrate's still floating around as a nitrate ion. They really haven't done anything. It is the cadmium and the sulfide that bonded together to make the cadmium sulfate. Okay, so how do we know? How would you know that this is cadmium sulfate and not ammonium nitrate? Unfortunately, you're going to have to memorize some rules. Now, this is the rule table from your book. We're running them down really quick. So it says sodium, potassium, ammonium compounds are soluble in water. And I would put in always soluble. Nitrates, acetates, chlorates are soluble. Chlorides are soluble, except those of silver, mercury, and lead. Oh no, this is getting a little bit more confusing. Sulfates are soluble, except barium, strontium, lead. Carbonates, phosphates, silicates are... you know what? This is a list. Okay, and sulfides are... So, again, these... There's nothing wrong with these guidelines, but they're not the easiest to decipher. I like this. This is a little bit easier. It's not... There's some things that I'll change on it, but for the most part, it is accurate and it's clear. And it's a little bit easier of a way to understand our solubility rules. So notice the first thing, start at the top and going down. These are how we want to try to remember our rules. So soluble. What's soluble? Group 1 metals are soluble. Alkali metals are soluble. So that's what this says. Sodium, potassium being soluble. Really, all of our group 1s for the most part are soluble. Notice no exceptions. Nitrates, soluble. Ammonium, soluble. So all of those things are soluble. No exceptions. Next one, there's a few exceptions. So group 7, that means our halides, our chloride, fluoride, those things are soluble. Sulfates are generally soluble, but now we run into some exceptions. And the exceptions we have to be careful of are these little bumps right here. So silver, mercury, barium, and lead. And actually for group 7, it's really just silver, mercury, and lead, but that's okay, I think, if we remember that all of these are generally our exceptions that we have to be careful of. Now when we get to the bottom, we have our insoluble compounds that we deal with. Carbonates, hydroxides, phosphates are generally insoluble. Now notice there's one time when they're not insoluble. That's if they're bonded to something up here. So this takes precedent. These things are always soluble. So carbonates can be soluble if they're bonded to something in that top of the pyramid. If they're bonded to an alkali metal, ammonium nitrate. Well, I guess they wouldn't be bonded to an ammonium, or they wouldn't be bonded to a nitrate, but ammonium are group 1 metals. Okay, that to me is a little bit easier way to understand our solubility rules. Now, it's not exhaustive. There's other things. Insolubility is one of those things that's not a hard, fast rule. There's variations if there's temperature variations, and some things can be very insoluble or just slightly insoluble. So it gets a little bit tricky sometimes, but I think if you know those rules, you'll do just fine. So let's look at this one. Will a precipitate form if solutions of potassium sulfate and barium nitrate are combined? Well, let's try that. Let's write it out and figure it out. So we have to be able to write compounds. Potassium sulfate. Potassium is K. Sulfate is SO4 minus 2, so it's K2SO4. Hopefully we're getting pretty good at being able to write these. Potassium sulfate and barium nitrate. Barium is Ba, it has a +2. Nitrate is NO3, so this is BaNO3. If they rearranged, what would they form? Well, this is a double replacement, so potassium with nitrate. We'd have K NO3, and our other option would be Ba. That's a +2. SO4 is +2, so BaSO4. Okay, So will it precipitate form? Going back to the rules, and first rule first, group 1 things are always soluble. Potassium is a group 1 metal, so it's going to be aqueous here, and it's going to be aqueous here, no exceptions. And notice, so are nitrates. Nitrates are soluble, so it's soluble by 2 rules. Nitrates are all soluble, potassium's all soluble, so it's always going to be soluble. This is always soluble because nitrates are always soluble, so we have to check out this barium sulfate. Notice sulfates here, it says are soluble, but we're in an exception column. Notice exceptions, silver, mercury, barium, or lead. Notice we're with barium. That is going to be our solid. And now we'd write our net ionic equation. Well, our net ionic, remember, is just going to concern the ions that are reacting. So I'm going to use my eraser, and I'm going to erase the potassium nitrate, because those are ions, they're not really reacting. The potassium is not really reacting, so I can erase that. Nitrate's not really reacting, it's just sitting in solution. So my net ionic would be barium plus sulfate, making barium sulfate. Okay, now you have some others you can try. That is the base. Well, we can do maybe one more. One more. They're kind of fun. We can do one more quick. So, will a precipitate form if we have solutions of potassium nitrate? So, K, potassium nitrate again. Okay, potassium nitrate. And magnesium sulfate are combined. Okay. So, what are our options? We can put our nitrate with our magnesium, Mg, NO3. And remember what our rules were. Nitrates are always soluble. So right off the bat, I can say that this is aqueous, right? This is aqueous. This is aqueous. So all those things are aqueous. So my other option then is potassium sulfate. Well, potassium, again, is a group 1 metal. That's always soluble. Sulfates are always soluble except with those exceptions. And this isn't one of them, so this is aqueous. So this really is not a chemical reaction. These are dissolved in water. These are dissolved in water. These are all dissolved in water. There's no precipitate coming out. It would not be a reaction. So just because we have a double replacement reaction written out like that, we are mixing 2 things, it doesn't mean that it forms a precipitate necessarily. Okay, we have to be cognizant of our solubility rules. Okay, one other thing when we're looking at solutions and we're looking at dissolution of ions is sometimes we have a process called ionization. Ionization is when we dissolve a molecular compound like hydrochloric acid in water and we get ions. Now, why does that happen? Well, it happens because that hydrochloric acid is polar. So not everything will ionize and form hydrogen ions, but polar compounds can when they react with the water. And so really what happens is when we have hydrochloric acid and we dissolve it, normally it's a molecular compound, it's not ionic, so it wouldn't normally form hydrogen and chlorine ions, but because it's with water, the hydrogen actually gets pulled away to the water, and we form an important ion that's going to get more important as the weeks go by, and we talk about acids and bases called hydronium, and we get chloride ions. So just to be aware of the ions that are actually in solution, we really don't have hydrogen ions in solution ever when we have acids, or when we have these molecular compounds that become ionized, we actually have hydronium. Now notice, not all compounds ionize that way. Sodium chloride is just a normal ionic compound that dissociates into sodium ions and chlorine ions. Notice sugar is a covalent molecular compound. It goes in water. It dissolves. The water molecules orientate themselves around it, but they don't take it apart. So it's not ionized. Hydrofluoric acid, like hydrochloric acid, does become ionized. The hydrogen gets removed, goes on to the water to make hydronium, and we get fluorine ions left over. Okay. Last thing in this unit is strong and weak electrolytes and the difference. Okay, so sodium chloride, a lot of our ionic compounds are what we'd call a strong electrolyte. Okay, what a strong electrolyte does is a strong electrolyte allows electricity to pass through the solution, right? It allows that light bulb, remember, on the top of this diagram to light up. Bing, bing, bing. So if I put some sodium chloride in water, mix it up, it all dissolves, and it's what we would call a strong electrolyte. The reason it's strong is because it fully dissolves, or what's called fully dissociates is the proper word. It fully dissolves, fully dissociates. Because it dissolves is not really the right word, because other compounds can dissolve, but not dissociate. So fully dissociates. So sodium chloride, when it dissolves, it is really an arrow that goes in one direction. We get sodium ions and we get chlorine ions. We don't have any sodium chloride stuck together in the solution. However, some things are weak electrolytes. They don't fully dissociate. So they might dissolve, but they don't fully dissociate. One good example is the one they just had, that hydrogen fluoride, HF. If we put that with water, now we will get some hydronium, which is an ion, which is an electrolyte, and we'll get some fluorine that will conduct electricity, but really, it doesn't fully dissociate. That's why we write this equilibrium. And if we want to be even more precise, what we'd do is we'd write the equilibrium this way. So a big arrow that way, a small one this way. What the small arrow means is we produce some of this, it partially ionizes this, and we get a weak electrolyte, but it doesn't fully. So full dissociation, if all the compound becomes ions, it is then a strong electrolyte. If we only have what would be called partial ionization or partial dissociation, then we're going to have our weak electrolyte. Okay. So, a couple of questions. Should we answer them? Yes. Write an equation for the dissolution of strontium nitrate, Sr, NO3, 2. Now I know that's going to be soluble because nitrates are always soluble. How many moles of strontium ions and nitrate ions are produced by dissolving 0.5 moles? So if we have 0.5 moles of this, well, we have 0.5 moles of strontium. And how many nitrate? Well, there's 2 times 0.5, 1 mole of nitrate. So this is where we just want to be able to read the equations we have. Next one. So it says, will precipitate form if we have magnesium acetate? So I have to write magnesium, Mg, it is +2, bonded to acetate, which has a -1 charge. So again, hopefully you can write your compounds out by now. And strontium chloride. If you can't, there's a little bit more work with them. Will we form precipitate? Okay, so we're going to have to go back and look at our solubility rules. At some point, I do expect that you memorize those solubility rules. That is the point. We can't go back and refer to the charts all the time. So we have magnesium with chloride, Mg. Cl2 is our one option. In a double replacement reaction, the other option is strontium with our acetate, Sr, C2H3O2 with a 2 outside. Well, what I can say is I know for sure that this is going to be aqueous. I know for sure because it's bonded to a halide, and those are generally, group 7 elements are generally going to be soluble. There's not many exceptions. We have to go back to look up this one, though. So, strontium acetate. We're wondering, is this soluble or not? Well, if we look at these rules, unfortunately, I don't see strontium, I don't see alkali earth metals anywhere on this list. I also don't see acetates. So unfortunately, this isn't, like I said, it's not an exhaustive list. It has our major things, but not everything. So I have to go back to the one in the book, unfortunately. But I do find that there's acetates here, and it says most are soluble. Okay, so most nitrates are soluble. So actually, maybe on this first tier, I want to add acetate, C3H3O2. So that's kind of unfortunate, but it can come up. This is our solid. Okay, so we did that. So we know what the solid would be. And let's go back and solve the rest of the questions. It says, what determines whether a molecular compound will be ionized in a polar solvent? Well, we didn't say much of that, right? We just had a brief thing. What is ionization? Well, ionization is like when we take the hydrochloric acid, we put it in water, and it becomes ionized, and it forms hydronium and chloride ion. So what determines whether or not that will happen? Because not everything is ionized and the hydrogens are ripped off of it. Well, it depends if this is polar. If this is a polar substance to start with, going in with a polar molecule like water, it's very likely that's going to be ionized. Next question is kind of more of the same. How's hydronium formed with a compound like hydrochloric acid dissolves, and what is the net charge? So the net charge on hydronium is that plus. It's H3O positive. It forms by basically the water going in, removing the hydrogen, and that's what we just wrote. So number 5, why is hydrochloric acid a strong electrolyte? Well, because it fully dissociates, or full ionization. In this case, I guess it fully dissociates, and HF is a weak electrolyte because it only partially dissociates. There we go. Partial dissociate. Alright, thank you. We got under 20 minutes. Bye.